And finally, I'd like to make you aware of our latest survey platform called Discover. Discover is a web-based, browser-based survey creation platform that doesn't just have the regular question types, such as single or multi-select, constant sum, but you can set up skip logic, quota control. You can very easily set up max diff or conjoint analysis in Discover. And the best thing is, you can give it a try for free. Just head over to sawtoothsoftware.com/discover. Yeah, thanks for, you can actually see it on the other slide here. So sawtoothsoftware.com/discover, and you can take a look at this fantastic tool. Now, if you have it open, you'll see a button that says try free demo. It's actually not a demo, it's the free version that has all the capabilities I mentioned, max diff, conjoint, etc. The only limitation of the free version is that you can field a survey with 50 respondents, but you can still go ahead and field it. All the capabilities are there, but it's perfect for you to play around with, see how powerful this survey tool is. It's fantastic, and it's becoming extremely popular very fast, very quickly. With all these announcements, I hope that we have all the people that are going to be listening. We are all ready. So I'm going to turn the time over to Keith. The screen is yours.
Thank you, Miklos. Okay, so we're going to talk today about the science and process of segmentation. I want to spend just a couple slides giving a little bit of background on what segmentation is. I'm going to spend most of our time, though, if you've had experience with segmentations, you've probably learned that they can fail. It's pretty common to do a segmentation study and for it not to be very successful. And so I want to talk about, there's a lot of things that make segmentation difficult. And I think a lot of the things that make it difficult aren't even things that a lot of people realize. And so they don't know there's even a problem to fix, so they can't go about fixing it. And then we'll talk about some tips for doing segmentation well, some tools and tips that you can use to hopefully have a higher success rate with your segmentation studies. So just by way of background, there's sort of, an obligatory slide that says what it is. We want to create groups such that respondents within a group or segment are similar to one another in some ways, and respondents in different groups are dissimilar. And the typical steps in a segmentation study, we're going to write a questionnaire that's going to include the questions that we need. It's going to include the basis variables that we're going to use to create the segments and the profiling variables that we're going to use to characterize or personalize them. Then we're going to create segments using those basis variables and some segmentation algorithms. We're going to profile the variables, use the segments using all the other variables in the study. Then we're going to go and be strategic about our segmentation. We're going to prioritize the segments and strategize about how to appeal to them or which to try to appeal to. And perhaps at the end, we'll add a typing tool for shelf life. But today, I really want to focus on just one of these. I want to talk about how we're going to create segments, because in my experience, maybe half the segmentation failures are in this bullet point right here. They're not so much in the other ones, although that still leaves plenty of failure to go around and reason to think about those other things. But today, we're just going to focus on this one. I talked about basis variables and profiling variables. And so typically when we talk about segmentation, we'll talk about, demographic segmentations or psychographic segmentations, behavioral or needs-based segmentations. At least in my experience, any one of these can make for a good set of basis variables, and any of them can be good profiling variables. And I hear people poo-poo demographic segmentations from time to time. And later on in the presentation, we'll show you an example of a really successful demographic segmentation we did once upon a time. As well, I wanted to mention that there's nothing that would prevent someone from taking 5 of the demographics, 3 of the psychographics, and 2 behaviors and saying those are my basis variables. We do segmentate. I would say probably 70% of the segmentations I do have mixes of these rather than sticking to just one of them. Okay, so what is it that makes segmentation difficult? I'm going to talk about seven different topics here. There's a couple of really vexing combinatorial problems that we face when we do segmentation. There's a cluster of problems that are all related or interrelated. There's a problem about sample size, about having too many variables that leads to something called the Curse of Dimensionality. There's some little known problems that can affect segmentation adversely and we'll cover those as well. Masking variables and correlated variables. Guess what? If you don't look for them, you don't find them, and they harm your segmentation. Having unequal segment sizes can be a problem, but there's a little bit of a way to address that we'll talk about. Response biases can cause some real difficulties in attitudinal segmentations. And then there's some client occult beliefs, I think, that we have to try to get our clients, try to move our clients away from them because they lead us down, they lead us in bad directions. Okay. So let's talk about those combinatorial problems. One is kind of in the nature of segmentation itself, and one is in the interactions that the analysts have with clients. So let's talk about the first one first. This is the Fiendish combinatorial problem. Let's assume that we have a really small segmentation study. We've got 150 respondents, and somehow we have reliable information that there's exactly 4 segments. Maybe we had a dream last night, or a revelation, or Nostradamus told us that we have 4 segments, or whatever. But somehow we infallibly know that there's just 4 segments. You'd think that this might make our job doing segmentation easier. Turns out there's 2 times 10 to the 90 ways of dividing those 150 respondents into 4 segments. There's a lot of solutions to look for. In fact, that's more ways than there are atoms in the universe. In fact, it's 500 million times more. There are 500 million times more possible solutions to that little segmentation problem than there are atoms in the entire universe. So that clearly we're never going to be able to look at more than a tiny fraction of the possible solution space. We're not going to be able to investigate all of them. And obviously it's even more daunting in a typical segmentation study where we might have 1,000 respondents, because now there's 10 to the 602 ways of dividing those respondents into segments. So it's a substantial problem. That was the Fiendish combinatorial problem. The devilish one is, let's assume that our study has 50 variables. Well, some of these are going to be basis variables that we're going to use to define our segments, and some are going to be profiling variables. Turns out there's 1.12 trillion ways to separate your variables into those 2 groups. And this is where I've seen scope creep come in a lot in segmentation studies, especially when we're using judgment rather than theory or analytics to guide our variable selection. So maybe the client says, well, let's try segmenting on variables x1 through x20. And if they don't like the solution, well, let's try x1 through x10 and x30 through x37. And if that doesn't work, well, we've got lots and lots of other combinations to try. And I've gone through this cycle of trying to pick basis variables. I think my record with a client was about 22 times cycling through this, trying to find the right set of basis variables. So this can be a really annoying problem. Okay, next is the cluster of problems that have to do with sample size and the number of variables. So let's just imagine a segmentation study that has 20 basis variables, and we want to allow there to be up to 5 segments. One recent reviewer suggests that we need a sample size at least 10 times the number of basis variables times the number of segments, so we'd need 1,000 people for this. A more recent review did a more thorough analysis, and they thought that you really need 100 times as many respondents as you have variables. So you take your number of variables, you multiply it by 100, and that's the sample size you should be shooting for, 2,000 in this case. I mean, a lot of our consumer studies, it's not too hard to get these kind of sample sizes. In some of our B2B studies, it can be really tough to get even 1/10 of those sample sizes. So there's going to be pressure, clearly, that since the sample size depends on the number of variables, there's going to be a lot of pressure to keep that number of variables small if we can. Another reason that we want to keep the number of variables small is, and my friend Joe Retzer pointed this out to me. He says, if you have just one variable, it's really easy to divide respondents into high and low scores, right? If we have a sample of people, we can pretty easily divide them in terms of their height or their education or their income. We can draw a median line, and we got a high and a low group now, right? Or a high, medium, and a low group. When you add a second variable, it becomes harder. And when you add 5 or 10 or 20 variables, the more variables you add, the less likely it is that your segments are going to be able to produce high and low scores on all the variables. It's just not going to be feasible. And so what you're going to end up with, if you have lots of variables, you're going to have segments that don't look very different at all. And the reason for that is something called the Curse of Dimensionality. Turns out that the volume of the segmentation space increases exponentially with the increase in the number of variables. So if you think about it, if you have just 2 variables or 2 dimensions, then the volume of space gets squared. But if you have 20 dimensions, it gets raised to the 20th power. There's a nice quote I like about this problem. Having too many dimensions causes every observation in your data set to appear equidistant from all the others. If the distances are all approximately equal, then all the observations appear about equally alike and equally different, and there's no meaningful clusters that can be formed. I've seen some hints that this maybe affects cluster analysis more than it does latent class analysis, but it definitely affects both. So, and at least I wondered, I didn't know why this was happening, but it seemed to happen to be a lot. I threw a lot of variables in my segmentation, and they wouldn't all be, I would have segments that looked approximately alike. There were a lot of very small differences. I think that's because the curse of dimensionality is coming into play. So a couple different reasons to try to keep your number of variables small. In addition to the number of variables, the type of variables you're segmenting on matters. Because if you include in your segmentation variables that the segments don't differ on, all they do is they make whatever cluster structure is in your data, they make it harder to find. They mask it. And that's why Briscoe called these masking variables, which seems like a really good name for them. And certainly, my friend Joseph White and I did a paper at the Sawtooth Software Conference, which you can download, by the way, from our website in 2021, where we showed just how much harm masking variables could do in terms of recovering a known segmentation structure. So these are really damaging. They're really good to get out of your data before you include them in your basis variables. But again, if you don't look for them, you don't know they're there, and they're just doing unseen damage to your segmentation. Another one, and this is a little bit counterintuitive, or it was to me, has to do with correlated variables. Because a lot of us came up, we do factor analysis, and we realized that multi-item scores are more reliable than single-item scores, and so on. And so we think in terms of having correlated variables, or it might actually make things better. In fact, it makes things worse. Because having correlated basis variables also makes the cluster structure harder to find. And when Joseph White and I found that in 2021, we really scratched our heads because we weren't aware that was the case. We thought, hey, we were surprised by it, but it turns out some other authors had already found it a few years earlier. So this is another thing to look out for. Not only do we not want masking variables, we also don't want correlated variables as our basis variables. So we need to get those out as well. Another problem that's I think pretty well known. The first reference to it I could find was from 2006, but Joseph and I, we found it as well. Some segmentation algorithms struggle much more than others to identify segments when the segment sizes are unequal. So we had a data set where we knew, because we programmed it in, what the segment membership was. And what we saw was that if the segment sizes were all equal, a lot of methods did reasonably well at reproducing that cluster structure. But when the segment sizes were very unequal, really only a couple of the segmentation algorithms we looked at did a creditable job at all. Especially the two that worked especially well were Sawtooth Software's CCEA program for cluster ensembles and latent class clustering. Those were the two that really did by far and away the best. I guess not far. There was one other method, a robust k-means method in R, that worked not quite as well as those two, but better than the rest. So maybe those 3 methods were ways of handling uneven segment sizes. Because really, we don't want to prevent unequal segment sizes from happening. If the segments are unequal in size, that's worth knowing. But we don't want to use an algorithm that throws us off the right answer. So we want to be careful there. Another thing that can cause problems with segmentation are response biases, especially if we're doing a segmentation based on rating scales. The fact that different people use rating scales differently, we all know that there's high raters and low raters, right? We know that people from different cultures use rating scales differently. Back in the days of mail surveys, we know that right and left-handed people used rating scales a little bit differently. So it's not at all uncommon for an attitudinal segmentation to produce a 3-segment solution, a segment of high raters, a segment of low raters, and a group of folks that are in between. Obviously, that's not a very interesting solution. We're segmenting on the artifact, the artifact of how people use rating scales, and it's masquerading as segment structure, a cluster structure, and that's obviously problematic. If we had a good way of subtracting out that response bias, it would be great, but it's harder to do than you would think. It's not just a matter of subtracting out the mean or something like that. Sometimes you're throwing in so much information away when you do that you've thrown out all the signal and retained the noise, and so that's sometimes not the best thing to do either. What I found is if we're going to use attitudinal, if we want to do attitudinal measures rather than rating scales, we might want to use something more like a max diff that's going to get rid of that response bias for us, and that's something that my colleague Dean Tyndall talked about, I think last month at our webinar. Okay, and then I wanted to talk about a couple of occult beliefs that clients have, and the first one, the second one listed there, clients just don't seem to realize that there's any limit to the number of variables you can include in cluster analysis, and that's because mathematically there's not. Even if we had just 50 respondents, we could have 1,000 basis variables if we wanted, and cluster analysis is going to work, and it's going to give us segments. They might be garbage, but it's going to give us segments. Mathematically, there's kind of no real limit on the number of variables, but given the things that we've talked about, the curse of dimensionality in particular, we really want clients to get off this thought that, well, we can just throw everything in the garbage can and things will turn out rosy, because it's probably not the case. Another occult belief that I have to deal with a lot is that I think a lot of people, once upon a time when they learned cluster analysis, they almost learned it, hey, you've got to do factor analysis and then, take your factor scores and cluster on them. That this, what's called dual clustering or factor clustering. A lot of my clients seem to think they need to do that. And I think it's a really bad idea, usually. And the reason is factor analysis it really doesn't produce what we need it to do for clustering. And so let's talk about what factor analysis is. It's a psychometric tool for identifying the underlying dimensions in a set of variables. And it's specifically used to test theories about what those underlying dimensions or constructs are, and theories about how to best measure them. That's what factor analysis does. That's what it's good at. It's not good at identifying the variables that might differ across segments. It's certainly not a solution for a garbage can of variables. If I got a client who tossed in, 174 variables, and they say, well, just cluster analyze it first, and we'll use the cluster scores. That's typically not going to work very well for you. And therefore, it's really not valuable for segmentation. So let me show you an example. Here's a study where I'm ordinarily loath to use rating scales for segmentation, but here's a study where we actually had some psychometricians design a segmentation, the set of questions. So they were relative, much better designed than your average set of questions would be. And we got this factor analysis, and the client said, well, we'll do factor analysis, and we'll use the top item from each factor. We'll use those as our basis variables. So those would be the ones in red here. Variable 10, 1, 11, 4, and 3. However, that didn't produce a very good cluster solution. When we cluster analyzed it, and what we really found was that the two variables that did the best job of showing differences among the segments were two of the items that were cross-loaders in the factor analysis, Q1_8 and Q1_7. And I've seen this happen again and again and again. We pick the top item from each factor, and we thereby miss the items that are best for cluster analysis. And that's just because the goals or objectives for factor analysis aren't the same as they are for cluster analysis. So the whole idea of doing this tandem clustering, where you factor first and then cluster, is just it can lead you down some bad alleys. So it's good to kind of tell your clients that that's not really a great idea. Okay, so we've talked about the things that make segmentation difficult, that in my experience, that make it fail a lot of times. And I'll say one of the reasons I put this presentation together is I've done hundreds and hundreds of segmentations, and I've seen them fail for a variety of reasons. And so I wanted to try to, put down on slides here where a lot of that failure comes from so that maybe we can have more success in the future. Okay, so now we're going to talk about what we can do given those problems, those, variable and analysis related problems, and ignoring for today all the other problems that could occur. How might we solve some of these problems? How could we do a better job of segmentation? And so here's the things I'm going to talk about in the following slides. I think I always feel more comfortable if I can preview my data and try to figure out before I even begin if there's, how much structure I'm looking for in the data. Do I have well-structured data that's ready for clustering, or do I have, do I have fairly unstructured data where I'm going to be essentially making stuff up when I segment? We should plan our analysis to deliver on objectives. And, a lot of times I'll hear from a client, well, we always use cluster analysis, or we always use latent class analysis for our segmentations. And as I'll show you in a minute, that's a mistake because you don't always want to use one method for your segmentations, because different kinds of objectives require different kinds of methods. I think we want to precede our clustering with something called variable selection, because we want to reduce the number of variables and break the curse of dimensionality. We want to reduce the stress on our sample size. We want to eliminate any masking variables or redundant variables from our analysis, because those cause problems. Those help us not see the true structure in the data. And so we really want to work hard to get rid of them. We'd like to use measures that avoid response bias, like avoiding rating scales if possible. We'd like to educate our clients to immunize them from those false beliefs, because those false beliefs are going to lead us down some bad alleys. And we want to use segmentation methods that are most likely to find structure. Like when Joseph White and I tested this, the two that did the best were the cluster ensembles in Sawtooth Software's CCEA package, and latent class clustering. Those both did the best job of finding structure. So in terms of previewing my structure, there's a really good segmentation book that I'll tell you about at the end by Dolnikar et al. From 2018. And they said, really, we should be looking to see if you have a natural cluster structure, kind of, no matter what we do, we're going to see the structure because it's going to keep coming out again and again and again. Or maybe we have to look a little bit harder and do some robustness testing and some reliability testing and find a reproducible cluster structure. Or maybe our data is really hardcore unstructured and we're going to have to impose structure on it. Later, some other authors did a review and they looked at 32 segmentation studies, and they thought that 6% of them had a natural cluster structure that was easy to find, 72% of them had a reproducible cluster structure, and 22% had unstructured data. And I'd have to say, when I think about my experience looking at data structure for segmentations, that's pretty much what I see in my practice as well. If anything, I find fewer studies that have a natural cluster structure, and maybe a few more that have unstructured data, but maybe I'm just unlucky. There's a couple of statistics we can look at to find out how much structure's in our data. The one I really like is called the Hopkins statistic. And there's some values there. If the Hopkins statistic is less than 0.3, you've got evenly spaced data throughout your multivariate segmentation space. If it's around in the neighborhood of 0.5, you've got random data. And if it's greater than or equal to 0.7, you've got nice clumpy data that segmentation can work with, and you've got happy segmentation algorithms because they've got what they need to do their job. Alternatively, you could look at the silhouette number that also tells you whether you've got anywhere from having no structure at all to having a very strong structure. And again, this is just kind of a preliminary thing I do before I start clustering. I look at this and let my client know, give them a feel for how hard we're going to have to work to find our clusters or our segments. The next bit of advice I have is make sure we match our objectives to our data conditions and to our, So we want to match our objectives and our data conditions. And so I've got this little segmentation flow chart I put together. This is kind of the map in my mind of the decisions I go through. So the first question I ask myself, is a choice model going to be the basis for my segmentation or not? Either it is or it isn't, and that takes us down two paths. If it is going to be the basis for my segmentation, is it going to be the only basis? Or am I going to want to put my choice model results plus some attitudinal stuff or plus some behavioral stuff in there? And if it's the only basis variable, then we can run latent class multinomial logit. That's something you can run in Sawtooth Software's Lighthouse Studio program. You can run it in our standalone CBC latent class program. You can run it in R. You can run it in latent gold. You can run it, and there's other places as well, right? You run it in nlogit and all sorts of places like that. Biogeme, I imagine. If it's not the only basis variable, then as far as I'm aware, the only game in town is to run it in a software package called Latent Gold, because that allows you to build segmentations based on choice model variables simultaneously with other variables. It's a particular kind of latent class multinomial logit model they have, and that's kind of a neat thing. Down the other path, if we're not going to be using a choice model as the basis for our segmentation, we should. My next question is there going to be a dependent variable? Is there going to be some variable that we want to see differ across our segments? Some one particular variable, and a lot of times it's like we're doing this for new product development, and it's like a purchase intent variable or something like this. Let's come up with segments that are going to be differentially, that our new product is differentially going to appeal to. And so if I have a dependent variable, I might go with a supervised or tree-based segmentation. If I don't have a dependent variable, I'm going to be going with an unsupervised segmentation. And if I don't really want to have a supervising variable, but I still want my segments to differ a little bit on some one variable of interest, I could do something called a predictive segmentation. If I'm going the unsupervised or the predicted route, I should at least ask myself, do I have a number of respondents that's greater than 100 times my number of variables? But whether I answer that yes or no, because we don't really know at this point whether we have masking or redundant variables, we should really be doing some variable selection. And we'll talk a little bit about how you do variable selection in a couple minutes. Once you've gone through that variable selection phase, you've gotten down to a very much more limited set of variables, and you're ready to start clustering. And so the next question is, are all my variables metric? Are they rating scales or binaries or counts or proportions or whatever? Or are some of them categorical? If they're all metric, I can go ahead and I can either do cluster ensembles analysis in Sawtooth software, or I can do latent class analysis. Maybe I want to do model-based clustering in R, is what it's called there. I have a choice. If my variables aren't all metric, if some of them are hardcore multi-category categorical variables, I really shouldn't be doing cluster analysis at all using cluster ensembles or k-means or hierarchical clustering. I should really be doing latent class clustering. And so that's kind of the decision tree there. But what you can see, there's 5 ending buckets there of methods for doing cluster analysis. And so anyone who says, well, I always do latent class, well, I don't always do latent class because sometimes I'm doing a supervised segmentation. Or I don't always do, latent class because what I really need to do is a latent class multinomial logit because I'm using a choice model. And so I really think we need to think harder about how we're going to, rather than fit everything, all segmentation studies, they always have to be amenable to latent class analysis. I don't think that's the case. I think that's a mistake. It's a very limited way of thinking about cluster analysis or segmentation. Let's talk a little bit about supervision. I mentioned that word on the previous slide. And I mentioned that we've got supervised and unsupervised segmentations, as well as one that's kind of in the middle that I call predictive segmentation. So in an unsupervised segmentation, this is what we usually have when we're thinking about doing cluster analysis or latent class analysis. We don't have a dependent variable that supervises or guides the analysis. And again, we might be doing cluster analysis or using hierarchical or k-means or partitioning around medoids or cluster ensembles if we're wise. Or we could be doing model-based clustering or latent class. A supervised segmentation, on the other hand, is we want to generate segments that are maximally differentiated with respect to some dependent variable. And that dependent variable is said to guide or supervise the analysis. And for this, we're going to use a tree-based method, and there's several to pick from. I'm old, so I started doing it back in the 80s, I guess, and the only algorithm I had at the time was something called AID, the Automatic Interaction Detector. It was an old DOSy program, but it made trees for me. And in fact, it made one of the most successful segmentations I've ever done in my life, this one here. I've disguised the variables a little bit, but this is a tree-based segmentation I did for a satellite TV company back in 1990. They had the idea that they could compete with cable companies by offering programming shot directly to people's homes, but they didn't know who their target market was. So we did a demographic segmentation. We collected all sorts of demographic. Well, to be fair, we also collected psychographic stuff, although it didn't end up, being part of the segmentation. And what this did is we used the people's anticipated spend on satellite TV programming as our dependent variable, and then we just looked for what the demographic or demographic or psychographic predictors were that best split that sample into groups, and we ended up, the sample split first on gender, then on age and income, and then finally on education, so we could come up with some target segments. Like over on the leftmost box there, we see that our best target segment were the young men who were going to spend an average of $914 a year on their TV programming, versus the lowest segment we had were the medium and low income women who were only going to spend on average $201. And then there were several groups in between. So we were able to, and not only did we define these, so now we define these groups demographically, they're going to be very easy to target, but we also had a lot of psychographic information about them, and we could figure out what it was they were wanting to spend this money on. Unfortunately, that young male segment, they really wanted to watch all of their sports that were televised, and all the ones that weren't televised. They wanted to watch sports, drink beer, and not work. So they didn't really have money to pay for all that programming they were going to buy, but they wanted it anyway. And it turned out to be I say this was a successful segmentation because the company launched, they became DirecTV later on. And for many years, if not still currently, they were the leading satellite TV provider. So I felt pretty good about this segmentation. In between the supervised and unsupervised is something I do a lot called predictive segmentation. So we want our segments to differ on some variable X. Maybe it's intent to purchase a new product, but we don't want to do supervised segmentation. And oftentimes, we're not wanting to do supervised because we don't really have the sample size that you need to do a good, you really need to have 1,000. Usually I like to ask for at least 1,000 respondents when I'm doing those supervised segmentations. And sometimes I can't get that. So the way this works is we're going to look at all the correlations between variable X and all of our potential basis variables, or alternatively, I like to use random forests to predict X and find my potential basis variables there based on the importance they have in the random forest. In either case, I'm going to take my basis variables that are highly related to X. I'm only going to use those as my basis variables. So if I might have looked at 300 variables, but I found 20 that are highly correlated to X. I'm going to use just those 20 in my segmentation. And guess what? My resulting segments are very likely to differ with respect to X. I've just found this to be a really useful way to do segmentation in support of new product development and targeting. I think variable selection is the thing that most commonly analysts don't realize they have to do. And we've gone over the reasons for it, right? We don't want to stress out our sample size. We don't want redundant variables. And we especially don't want masking variables in our data set, because all of those things, the redundant and the masking variables are really tend to, as the masking name suggests, hide the structure data, the data structure from you. So you're likely to miss the real segmentation structure in your data because you've got all these noise variables in there. And the thing is, they don't just provide random noise, they steer you in the wrong direction. So it's important to do this. And maybe, all that coaching worked and the clients provided us a nice short list of basis variables that don't include redundant and masking variables. But of course, we don't know that. So I still think we need to do variable selection. How do we do it? At the Sawtooth Software Conference in 2021, Evan Owakowska and Joe Retzer talked about something called biclustering. I'd encourage you to get the conference proceedings and look at their paper because I thought it was a really good one. I had never heard of biclustering, but while it's got some drawbacks, it's also kind of a neat method. So take a look at that. There's automated variable selection methods we can use. Joseph White and I tested one called clustvar-cell. That did a really, really powerful job. We were able to show that, getting those masking and redundant variables out of the analysis allowed us to have a much better chance of finding the true cluster structure in data, which was kind of cool. And that was in our, I think that was in our 2022 paper, Joseph White's and mine, in our Sawtooth Software conference proceedings. So check that one out. Really nice paper that Joseph put together. And then last year, because I oftentimes face kind of garbage can sets of variables for my clients that are a mix of categorical and metric variables. After ClusVar Cell worked so well for us, I looked for a variable selection program that would handle mixed variables. And I found one in varcell LCM that worked really, really well. Both of those methods are available in R, by the way. And then lastly, my colleague Joe Retzer recommended that I look into unsupervised random forests. And I had never heard of an unsupervised random forest. It didn't make intuitive sense to me. But when I looked into it, it looked pretty cool. And actually, we've discovered that it works pretty well. Next to varcell LCM for mixed metric and categorical variables, it did the best job. So what is unsupervised random forests? What we're going to do is we're going to combine two data sets. We're going to take our actual data file and we're going to append a new variable that we're going to code 1. And then we're going to take an equivalent data file, but each variable has its values independently drawn from the same distribution that variable has in the actual data. And by independently drawing the variables, this breaks all the relations between the variables. It breaks all the structure in the data. And this second data file, we're going to slap the new variable on and we're going to code it too. And now we're just going to run random forests to predict that new variable using all the other variables. And this is going to identify and give an importance. It's going to quantify the importance of each other variable in terms of predicting the structure in the data. You don't have to actually do all of these steps. The program for doing unsupervised random forests in R does them for you. And it as its outputs, it gives you a proximity matrix that you could take and directly use in clustering if you wanted to. But it also gives you a list of variable importances that you can use to manually do variable selection and then to go on and do whatever clustering you want in whatever program you want. And I found that just using those variable importances can really improve your segmentations if you've got masking and redundant variables in there. Kind of cool. My last, my next bit of advice has to do with using robust methods. We know that different segmentation methods produce different solutions. You can take the same method and run it on the same data, but with different random starting points and get different solutions. Sometimes in some software packages, if you just change the order of your respondents, you can get different segmentation solutions. And because there's all this instability, we know that we should really not use a simple thing like fastclust or quick cluster in SPSS or fastclust in SAS. We should really do methods that seek out convergent validity. And the methods that do that are the Sawtooth Software's Convergent Cluster Ensembles Analysis, CCEA, and model-based clustering, or latent class. Those seem to work really well. There's another kind of a brute force, robust version of k-means in R that also works pretty well, but not quite as well as CCEA or model-based clustering. So that's my advice there. And just because we talked a little bit about latent class analysis, I just had this last little slide here about latent class analysis. Whereas cluster analysis is looking for people who have similar scores on the basis variables and saying that people who are similar with respect to their scores belong together, latent class analysis is actually a probabilistic statistical model that has stat tests and native fit statistics you can use. Whereas cluster analysis is just a mathematical model with some fit statistics bolted on. So latent class is really nice. It assumes that there's hidden classes or segments that are mixed up in your data in such a way that they produce the patterns of data that you see. And what we need to do is to unmix that data. And so latent class analysis uses an EM algorithm to unmix the data by identifying a new variable, class membership, that explains the observed data pattern. And it's the quality of that assignment is measured by something called the Bayesian information criterion, which can help you identify the number of segments that you have. So latent class analysis is kind of cool. Before we turn it over to questions and for Miklos to close things out here, I should mention Sawtooth Analytics is someone who can do segmentation for you. We do about 100 consulting projects a year for clients, or a little bit more than that, I guess. And a lot of them are segmentation. So we're available to help. If you need help with your next segmentation study, I'm Keith at sawtoothsoftware.com. So feel free to drop me a line. I just wanted to go through some references here. I've got a lot of them that I referenced in the paper. A really good one is this book called Market Segmentation Analysis, Understanding It, Doing It, and Making It Useful. And another nice thing about this book is you can get it for free at that website. You can, it's an open access book, so you can download it for free, and it's well worth reading if you do a lot of segmentation. With that, I think it's time for questions.
Yeah, thanks, Keith. Great job. And if the participants still have a little bit of a time, what I'm going to do, I'm going to kind of go through a couple of questions. We got a lot of questions, and we have Dean and Christina answering some of them. But I think some of them would be good to kind of read out and see if Keith can help with some of them. Let me start with the first one, which was by Mike Bone. He was talking about the correlated variables. And the damage they can do to make it difficult to uncover the cluster. Since there will always be some level of correlation between two variables, what do you typically prefer as a standard threshold for deeming it as too high of a level of correlation to include as basis variable? Stricter threshold like 0.8 to 1, or looser like 0.4 to 0.6? What do you think?
You know, I don't know the answer to that, because I usually use those automated variable selection procedures that get rid of the correlated variables for me. What I know is that when Joseph and I did our test with artificial data and known segment structure, what we considered correlated variables were in the range of 0.6 to 0.7. And even those were detrimental to cluster structure, and even those were identified, pulled out, and removed by the automatic variable selection technique. So I really, it's an interesting question. It just, this topic is so new to me. I haven't really had time. It would be interesting sometime to put together a data set that, where does the problem start? Is it correlations of 0.6 like Joseph and I found? What about 0.5? What about 0.4? At what point does it cause problems? And at what point do the variable selection techniques catch it? And I think we don't know either of those answers yet. So there's a possible topic for someone to come present at the next Sawtooth Software Conference if you want to look into that.
Okay, thank you, Keith.
Great question, by the way. I didn't even think about that. That's a really good one.
Let me move on with the next one by Jordan Lieberman. He's asking if you could explain a little bit better the difference between masking and correlated variables.
Okay. So a masking variable is one that the segments don't differ on at all. Maybe I've got segments that are different with respect to 5 variables, but when I look at eye color, for instance, my segments have the same distribution of eye color. So what's going to happen is if I include eye color as one of my basis variables, the algorithm is going to try to make groups that are different with respect to eye color. It's going to be one of the things, one of the bits of gravity operating in my segmentation method that my algorithm is going to try to pull segments apart in terms of eye color. But since because it's a masking variable, however, it's not related to the real structure in your data. And so that effort that the cluster algorithm is going through of trying to make segments differ on eye structure, even though it's irrelevant to the cluster structure, it's going to give you a different and less correct cluster structure. Whereas correlated variables, or maybe I've got a variable like, my propensity to buy a certain brand. And maybe that variable is an important basis variable for me. Other variables that are related to that, like maybe desiring the properties that brand has, or being in a certain age group that kind of likes that brand, those might be correlated variables that you might think are going to reinforce the structure in the data, but it turns out they don't. So that's the difference between correlated and masking.
Thanks, Keith. Here's a question that I think is a really good one. I think a lot of people probably have this question in their heads. This is by an anonymous attendee, but either way, he or she is saying, I'm confused about the names LC, latent class, because when I use CBC, I talk about latent class logit models, but it seems that latent class analysis is different. What's the difference between latent class analysis and latent class logit models?
That's a really good question. In fact, I kind of thought this was going to come up, and I had a slide in here earlier about that. Latent class describes an entire family of models. There's unsupervised latent class models. And then there's different latent class models depending on whether you have metric data. The original latent class had categorical data, and some purists still say you should really only use the words latent class when you're dealing with correlated data, and everything else you should call mixture models. But I'm not quite such a stickler for that kind of terminology. But you've got these we've got these models that are just based on the distributions of variables. But then we've also got latent class models that there's a latent class version of regression that simultaneously finds segment membership and differences in regression coefficients. The unsupervised latent class, the basic latent class, it identifies segment membership that produces differences in terms of your variables. Latent class regression, differences in terms of regression coefficients. Latent class multinomial logit, it's going to produce segments that differ in terms of their logit coefficients or their utilities. And you can see how that might be valuable. There's also, I've seen latent class versions of analysis of variance, latent class versions of perceptual mapping even. So, back in the 90s in particular, there was kind of a proliferation of latent class methods to do all sorts of things. But the ones that are useful for segmentation would be the basic latent class or mixture model that you can use with unsupervised data, or the latent class regression or latent class multinomial logit that we could use with conjoint or choice data.
Thanks, Keith. There are two people that asked this question, so I'm gonna pick this one. Do you have a stance on the recommended number of basis variables?
With the sample sizes I work at, I really like to. I know my clients often ask me this too, and I tell them, boy, I'd really like to shoot for something between 10 and 20. I'm not going to have if I'm only going to have two variables, why bother to do a segmentation study? You can run a crosstab, right, for two variables. But above 20, I think we start running into that that curse of dimensionality in a pretty bad way. So I really like to see us in the 10 to 20 variable range.
Okay. Alex Burns asked, this presentation focused on segmentation from surveys. Do you have a perspective on best approaches to segmentation that are not survey data? For example, customer purchase data with associated demographics, or would the approach be pretty much the same?
I think it's, although I spoke a lot in terms of survey data because that's what I've been working with for the past year, 10 years or so here at Sawtooth Software. I've been working with survey data. But before that, I did a lot of segmentations on client databases, right? So they've got a big database of people. It's got attitudinal, they might have attitudinal stuff. They've at least got behavioral stuff and demographic stuff in there. And the points I've made, I think, in this presentation would apply equally to that data as to survey data. The algorithms don't care where the data comes from. So I think those factors are the same, those success factors.
Okay, let's address a couple of more, maybe one or two more, and then we're going to have to close. And if you guys still have questions, please do reach out, send an email. We're happy to answer them. Let me take this one from Ethan, because I think Ethan is talking about a typing tool. So when choosing basis variables, we're also thinking about that they can be used as allocation questions after the segmentation is done. In other words, a typing tool. If I understand correctly, latent class multinomial logit models that use choice data, that should be a barrier to adopt, since it's a lot of effort to redo the choice exercise every time you want to categorize people. What are your thoughts on that?
That's a good point. And it is a lot of effort, although you typically don't need to ask the entire choice experiment. So for example, if you've done your segmentation based on max diff, we have at Sawtooth Software, we have a max diff typing tool. And what it does is it will come up, you'll put your segmentation data in there, and it uses something called a naive Bayes analysis, and it'll come up with a small set, typically 4 or 5 questions. It'll come up with a new set of max diff questions, and like I say, typically just 4 or 5 of them that you can ask in future surveys without reproducing the entire max diff experiment every time you ask questions. You get it down to this short list of 4 or 5 questions, and you can then use that to classify people into your choice-based segments. I think it'd be a little bit harder if you did this as a choice-based conjoint, because our naive Bayes tool doesn't do that, but you could program a naive Bayes tool in R to do it. I think there have been a couple presentations at our conferences where people, at least one, where people have talked about using naive Bayes and they've run it in R. So you might check that out.
Okay. I appreciate it. Thank you. We're going to stop here with the questions, and thank you very much for the answers. If you still have burning questions that have not been addressed here, please do reach out. At the same time, I'd like to thank Christina Miller and Dean Tyndall, who here in the background were quietly answering the questions, and I appreciate that. We had a lot of great questions. A couple of points before I close. Again, Keith mentioned that he leads our analytics consultancy group. Now, segmentation is very difficult, and I hope that you guys learned enough right now, the participants here, that you feel a little more comfortable and more confident doing segmentation. If you have a tough segmentation project come to you, please do reach out to Keith and Keith's group, and they'll be more than happy to help you. Keith's email address is very simple, keith@sawtoothsoftware.com. And he and his team regularly partner up with other consultants to help do some heavy lifting. So do not hesitate to do that. Normally, I get a lot of emails with this question, so let me address it right now. The recording of this webinar and the copies of the presentation will be available 24 hours after the event, and we will email you the link to participants as well.